Hello, everyone. Welcome. I'm Zander Majercik, and today I'll talk about optimizing a string class for computer graphics. So I work as a research scientist at NVIDIA doing computer graphics research. I mostly work on real-time rendering algorithms for games and more recently data center graphics. My co-author, Morgan McGuire, who is also giving a panel later today, is the chief scientist at Roblox, and he mostly works on everything. But as part of graphics research organizations, we wear a lot of hats, we do a lot of stuff, but fundamentally what we are is 3D game programmers. So we develop algorithms for games from the initial research prototype stage all the way to production code. So this slide here is showing a sampling of games, research papers, and SDKs that we've either authored or contributed to. In addition to being 3D games programmers, we're C++ professionals too, in that we use C++ every day when prototyping these novel graphics algorithms. So games and real-time computer graphics more generally are written in C++ because it's a great match for computer graphics. It gives low-level memory control, gives high performance, gives a modern object-oriented feature set, and there's a very robust ecosystem associated with C++. And graphics in games has some sort of familiar idiomatic use of C++. In fact, it's gonna, as you'll see in the code I show, it's gonna look a little more like C++ 11 or 14 because graphics code bases are, I think, a little slower to adapt modern features of C++. But one of the sort of, I think, idiosyncrasies of programming in graphics and games is that we use a lot of strings dynamically at runtime. And so here's how this happens. So here's a screenshot from a popular game. So there are some strings that are sort of more obvious. These strings appear directly on screen as user interface elements and as chat and dialogue. And in fact, most numbers that appear on screen are also usually UI text. So they're turned into strings on the back end and then rendered with the font renderer to be composited into the final frame. But strings also are doing a lot of work behind the scenes as localization tags, as strings used in networking, and also for code generation and argument binding for both embedded scripting languages within C++ and for programming GPU shaders, both of which I'll describe more in the following slides. So all of this taken together means we need high-performance runtime text manipulation, high performance that's at 60 frames per second or more, and across multiple platforms and operating systems, so Windows, Linux, and high-end PCs, all the way down to previous generation game consoles like Xbox One. So let's drill down specifically into how strings are used to communicate between the CPU and GPU parts of the program through a GPU programming API for computer graphics. So GPU programs are written in very restricted C-like languages, which are then compiled to device-specific code. And these programs in the computer graphics context are called shaders, and they involve a lot of runtime string work. So shaders are often composed from multiple code string segments and then compiled on the fly with runtime preprocessors. And then to run these shaders, you often have to pass data between the GPU and CPU, or at least provide the shader a reference to GPU memory that's going to be used in the shader code. And doing this data passing data between the CPU and GPU, often looks a lot more like a network API than a standard mixed language program. So strings are used here to discover the argument binding points and structure layouts for data being passed from the CPU to the GPU. And so I'll note in passing here that you could achieve the same thing, sort of this discovering these binding points for resources on the GPU by mapping GPU resources to static indices. But in game programming, we often prefer to use strings at every communication point because it massively increases programmer productivity. So this means you can map semantic string names to resources, to textures and such, which make things a lot more flexible. And so the result of this is that most of these GPU function calls, these shader launches from the CPU, look a lot like building a hash table with dynamically composed string keys. So here's a little bit of a code segment showing how that works. So the shader arguments are being set with strings on the args class at the very top. This is the first line. And this is basically the hash table that I just talked about, mapping these string arguments to GPU resources. And then finally, at the very bottom, this args class is passed in to the shader for final compilation. And so as far as string usage, the first thing to notice here is this set shader args call. And what this is basically a wrapper function implemented in our graphics engine for setting all of the GPU resources associated with that struct. So, in this example, this quote gbuffer underscore is going to be prepended to all of the different names that identify the different textures or different sort of memory on the GPU that are associated with that gbuffer. And so for each of those textures, you have string concatenation and construction of a new argument for every field in that hash table. And things work very similarly, actually, for if you're passing structs or arrays to the GPU. So in this case, each element is expanded out because they're packed directly into GPU registers. So for example, passing an object like a light here, like this struct, which you might use in a representation of a 3D scene, is going to turn into a bunch of string operations for each element within the light struct. So you'll get a string for light.position, light.color, and so forth. And the reason that, at least if you're setting it as a uniform, you can't pass a reference to the whole structure or do an opaque memory copy is the CPU and GPU often don't agree on the memory layout. And even if they did, the registers on the GPU aren't accessed as a memory block, but as individual binding operations in shaders. So what that means is, for an array, these elements of the array will literally become the strings, quote, array0, quote, array1 internally. So seriously. And as we'll see an example of sort of later on, scripting languages do a very similar thing for similar reasons. So returning to our text example, the next thing to notice for string manipulation is these macros. So macros are sort of normal C++ style macros, which we can use in shader code. These are often plain old data, sort of int, bool, float, what have you. And we can also, as uniforms, bind the vector variants of these data types, which we often do for graphics. So vector3, vector4, int vector3, int vector4, and so on. And so the final thing going on is this get shader from pattern call. And so this is the sort of dynamic composition of shader code that I mentioned earlier. So the beginning of this string can change at runtime to specialize on a different shader, which is then loaded, compiled, and run. So the whole text of the shader is being loaded into memory, the macro and include expansion is being performed, and the shader is compiled. And this can happen dynamically at runtime to reload changes to the shader. And in graphics and research specifically, we often use embedded scripting languages. In this case, it's Python for rapid prototyping. And so the mechanism operates very similarly to a shader launcher, except in the case of Python, what you're doing is importing modules and functions, which is then making another hash table, this time mapping these string names to PyObject pointers using the Python C API. So one thing to note with scripting that's interesting for strings is that with scripting, it's often the case that not only the function and variable names are strings, but the actual values are strings, which entails even more runtime string manipulation. And one of the reasons for this, in addition to the sort of register thing I talked about earlier, is that scripting languages often implement objects as hash tables with keys as strings instead of structs with hard-coded integer offsets for member variables. So after all of that taken together, here are the sort of properties of string usage in graphics. And these tell us basically the requirements that we want our string class to have. So strings in graphics are often small, they're often empty, they're often constructed by concatenating a lot of different smaller strings together. They're often constructed from const char pointers, and there are a lot of const segment strings. That is to say, strings with the text written directly into the program executable, which I'll talk about more later. And so looking at these, we see that what we need for our string class is a string class for highly optimized copy construction, concatenation, conversion or construction from const char star, and specifically we're focusing on small strings because that's the sort of use case for strings in graphics. And we want to support the full standard string API. Basically, it needs to fit into the standard string ecosystem. A lot of game engines use standard string, and what we want is a drop-in replacement for standard string that implements the full standard string API and is as performant as standard string for longer strings, but is much more efficient for shorter strings. So there are a bunch of optimizations that we can choose from for optimizing a string class, so I'll go over them briefly here. So we can do copy on write. Copy on write maintains a reference to the copied string and defers copying until the new string is actually mutated or the old string is mutated. We can do local storage for small strings. So this reserves a small amount of storage or buffer directly on the string object, which allows it to be allocated on the stack if it's a local variable. This is the small string optimization, or also small buffer optimization, what it's called. We can use like SIMD instructions, single instruction multiple dispatch, or vector instructions. These can be used to efficiently implement string operations, provided the string has correct alignment. We can alias const segment strings to avoid copying them in some cases, and I'll talk more about that later. And there's also early out optimization. So for a lot of string methods, we can do sort of a simple if test at the very beginning and maybe avoid a bunch of work by early exiting from the function if the condition is met. So our string class is called SIMDString. The original focus was on the sort of SIMD vector instructions, and it utilizes many of these. So here's an overview of it. So starting from the relevant properties for graphics that you're seeing here, we basically select the optimizations from that list that give us the best performance for computer graphics usage patterns. And so of these, probably the most impactful is utilizing the small string optimizations. This is having local storage on the class for small strings, and this also gives us fast empty string construction. And I'll note here that there are a lot of small string classes out there specifically that sort of only deal with strings of a certain length. But again, we want to be fully general. We want the behavior to be correct no matter the string size, and without knowing in advance what the string size is, we want to also optimize for small strings behind the scenes when possible. So the next two optimizations both have to do with char start pointers, and these are optimized by this aliasing const segment strings that I've been talking about that I'll talk more about in the following slides. And finally, we make copy and other operations as efficient as possible by ensuring correct alignment within the string class to make use of SIMD vector instructions. So there's sort of nothing revolutionary going in this code segment. This is the declaration of our string class. The two important things to note here. So our class is templated on the amount of internal storage. In this case, it's 128. We found the best results with 128 bytes of internal storage, but we tested 16, 32, and 64 bytes as well. And it's also uses the C++ allocator pattern, so it can be templated on taking an allocator. We use the allocator from our research engine, G3D. This is a small block free list allocator, low overhead, pretty reasonable cache behavior. And so most game engines will have their own allocator pretty similar to this one. So the point of sort of templating or having our class allowed to be templated on this allocator is not necessarily to sort of supercharge performance, but to make sure that sort of we can conform to that API so that when this class is used in a game engine, they can use their own allocator for it effectively. And the final thing to notice is that we're sort of ensuring the alignment specifically so that we can take advantage of SIMD vector instructions when appropriate. So I've been talking about sort of aliasing const segment strings for a couple of slides now. And this is sort of one of our most important optimizations, so let's look at it in some detail. Before I show the code, though, I'm going to give a sort of brief motivating example of sort of what happens for memory allocation for a couple of example strings. So how does the memory get allocated for these strings? Well, so starting in the middle, string AB is small enough that after it gets constructed from the concatenation of strings A and B, that those characters get copied into the local buffer and get stored completely on the stack. So there's no heap allocation there. String heap AB is too big for local storage. So after all of those strings get concatenated together, you have too many characters to fit in that local buffer, and so that does trigger heap allocation. And so then that heap AB string will store a pointer to that dynamically allocated memory on the heap. So what about string A and B? So in principle for string A and B, it's the same thing as string AB. So those strings are short, so the small string optimization will copy the data into the local storage. But the difference between strings A and B and string AB is that whereas string AB is constructed from a dynamically constructed string at runtime by concatenation of the strings A and B, both A and B are constructed from data that's actually baked into the data segment of the executable. And if you examine the executable, you can see it. So I used a program, this is from HXD, to examine the executable that contains the declarations of string A and B that you saw on the previous slide. And you can see that the characters of both strings are present in the executable. Specifically, this is on Windows, they're present in the rdata section of the executable. This consists of initialized read-only data. So for our purposes, there are two important bits about this data. One, it's not going to be modified by the program. So for two reasons. One is that, well, it's read-only data, it's kind of in the name. And also that modifying this section of the data would sort of, in principle, be no different from modifying the code section of the executable, which would be a security risk. And two, this data is often stored in a very high memory address. That is to say, a memory address that looks very different from heap and stack allocated const char store pointers. So what this allows us to do is optimize our SIMDString class by writing this function in const segment that takes a const char store pointer and detects whether or not it points to an address in this constant data segment of the executable and allows us to avoid copying it if that's the case. So here are the details of doing that const segment detection. So on Linux and MSVC, we can directly test pointers within the loaded image to see if the address of the passed-in pointer lies within it. And this is sort of the most principled way to do it, and we're going to be adding this for more runtime image formats. And on other compilers, and as a general fallback, and this is actually what we used for most of our tests, what we instead do is we probe a const segment address by initializing a string, a unique const segment string that you can see 3 lines up from the bottom, and checking its address. And we assume, pretty conservatively, that the const segment extends at least 5 megabytes on either side of that probed address. So then we check if the passed-in string is within 5 megabytes of the const seg address we probed. And if so, then we assume the string is in the const segment, and then we can do optimizations to avoid copying it. And this is relevant in a bunch of different string methods. This is relevant in construction from const charstar, string view construction. It makes comparisons super fast, because if you happen to compare 2 strings that both are in the const segment, all you have to do is compare the pointer addresses. And then also assign and replace. And it makes a pretty big difference for performance, as you'll see when I show results in a couple of slides. So it's worth asking, this is kind of a heavy-duty pointer hacking optimization. So why can't we just use const expert or standard string view to do this? And so here's one reason that sort of demonstrates, I think, the general principle. So here's a function foo that takes a string A by const reference and then copy constructs another string B before doing stuff with B. And so the copy constructor taking a const reference to string is going to be called here. So because we're in graphics and because we're doing string manipulation at runtime, this function might be called every frame with a different string. This means it could be called with a short, dynamically allocated string, or it might be called with a string that points to a very long const segment string. In the first case, we perform the copy immediately, and that's OK, because the string is small. In the second case, we really want to just alias the const segment string to avoid copying the entire thing until we absolutely need to, because depending on sort of what path we take through the code and doing stuff with B, we might actually not have to copy it. And we want to avoid doing it sort of automatically if we don't have to. And const expert, of course, doesn't work for this because the values aren't known at compile time. And string view doesn't work for this for 2 reasons. One, we need correct behavior in the case of the copy constructor taking a const reference to string, which is part of our code base already, even if we wanted to rewrite it to take string view. And in addition, even if we were constructing from string view, there's no way with the default constructing from string view to know that we shouldn't perform a copy from that string that's aliased in the const segment. So the other design patterns explored, we explored some other optimizations, and sort of these are sort of the ones remaining from the initial slide of options that I showed. Specifically, we explored using copy on write, but we found that basically the overhead of doing the reference counting wasn't worth it. In fact, we get like a decent amount of the benefit that I think you would have gotten from copy on write by doing the sort of pointer the const seg aliasing that we're doing, but without having to do a lot of the reference counting. And we tried for multiple string operations, we tried this sort of early out by sort of testing the out condition early to see if we could exit and avoid the sort of work of comparison and what have you for the rest of the string. But in our benchmark, we found that it was we got better performance basically without doing that. So we found that the overhead of the if statement to check the early out condition in a lot of cases wasn't made up for by the avoided work. And the sort of more I think about it, the more sense this makes, because we're optimizing for small strings specifically. So for each individual operation, the amount of work that we're saving by early out with an if statement is not going to be huge. So the sort of aggregate of sort of doing all of those if statements to sort of early out of all these individual operations sort of takes more time than it's worth. And for each of these, we were pretty exhaustive in our search. So we looked at disassembly, we profiled on multiple platforms. We just couldn't make either of these ideas work reliably, and so we didn't include these in our string implementation. So before I show some results, I want to discuss how we constructed our benchmark. So to test our string, we tested multiple string variants. We tested our SIMDString, templated on 16, 32, 64, and 128 bytes of local storage. We tested against standard string, of course. We tested against EA-STL string. This is the string implementation from EA Games. We also tested FB string from the Folly library from Facebook. And so to construct the benchmark, we profiled the frequency of string operations per frame in multiple different graphics programs showing basically a wide range of visual effects, so the sort of representative swath of graphics programs. And this programming gave us a relative weighting of string operations to determine basically which optimizations would have the highest effect on program speed. And so those operations that happen more frequently, sort of per frame in graphics programs, are sort of weighted higher, more importantly, into the benchmark. And so then we integrated this into Google Benchmark and tested on string sizes from 0, so the empty constructor, all the way up to 2 megabyte strings. So here's the first table of performance results. This is our SIMDString template on 128 bytes against standard string. And so I'm testing the constructor, I'm testing copy construct, I'm testing copy construct from const char and also concatenation. Those operations are on the x-axis, and the y-axis is time in nanoseconds. So the first thing to note here is that we're basically the same as standard string. We didn't really do a lot better. But that's actually good. That's good because this is testing 2 megabyte strings. These strings are huge. And because we're looking for a drop-in replacement for standard string that performs no worse for longer strings and is much better for shorter strings, the fact that we're basically the same as standard string is actually very good for us. And there's much more of a difference if you look at shorter strings. For example, if you look at 32-byte strings. So this is the same graph. The y-axis is again time in nanoseconds with the operations on the x-axis. And I've kept all the operations from the previous slide, construct, copy construct, C star, copy construct, and concatenation. I've also added the const C star construct. This is specifically doing the string construction from a const star pointer that points to an address in the const segment. And the speedup from this is the sort of most dramatic one. This is because what this operation does is it just verifies that the pointer is in the const segment and then does a pointer copy and a copy for the length. So that's it, no matter the size of the string. So that's why in sort of the final column, the speedup is the most dramatic. So on these, which are the most important operations, we get anywhere from a 4x to more than 10x speedup over standard string for these common operations. And then finally, here are the performance results for those string operations against all the competing implementations. And I'll note here that I'm showing just these operations because these were sort of the motivating operations for us, given the performance, the usage of strings for graphics. But we tested the sort of full pantheon of string operations, and that'll be included in the code that I show, or that'll be included in the code repository that I show at the end of the talk. And so this is, again, showing 32-byte strings. Each the same operations are here, time in nanoseconds on the y-axis. And this is showing our SIMDString templated at 16, 32, 64, 128 bytes against this time ASTL string, standard string again, and then Folly's FB string. You can see that on whatever measure of local storage that we template on, our SIMDString is outperforming standard string and also ASTL string and Folly's FB string. So, in this talk, I presented FB string. I presented SIMDString. Our SIMDString achieves about a 5x speedup taken in the aggregate over the whole benchmark of operations, not just what I showed here, about a 5x speedup over standard string, and also speedup over previous state of the art. And it's used in research, in our research graphics engine G3D, and also in production at Roblox. And so even outside of those domains, it's been used in computer graphics research and involved in production for nearly 20 years. So variants of the string have been kicking around in graphics for a very long time, much longer than I've been working on it. So it's not as if this is something that we tested that's kind of very fast on one processor and gives good results in this one domain. It works well across architectures and different OSs. So what I'm presenting here today is kind of the tip of a very large iceberg of development on this string class that has been going on for a long time. Second, though our string class is optimized for graphics, I'm hoping that our method serves as sort of a case study for string optimization in other domains. Maybe you find some of the sort of benchmarking code that we wrote useful. Maybe sort of the method is something you can take something away from. And finally, it's really cool to be able to present this work at CppCon. This is a completely new venue for myself and my co-authors, and I'm hoping this is the beginning of a lot of sort of more collaboration and knowledge transfer between the C++ and computer graphic communities. So before I close, I want to give a big thank you to Lin Wan Song, Tony Liu, Roberto Paulin, Corey Taylor, and Andrew Lacey, who are all instrumental in getting the benchmarks running and getting the code repository up and running. And finally, to the Williams College Computer Science Department, where I first started working on this project many years ago as undergrad. All right, here are the ending resources. Thank you very much. I can take questions now.
I was just curious if you ran your benchmark for smaller strings where the STL buffer optimization would actually work.
Sorry, say that again?
So the string, the 32-bit, I assume that it's just too big of a string for the buffer optimization that STUD-string does to kick in. But if you take something smaller, I would expect that they would compete with your implementation.
Repeat your question. So the question was, for 32-byte strings, it might be the case that that's too big a string for the optimizations that the standard string does. For smaller strings, and that like a 16-byte string might be more fair comparison. So I believe, first off, so in the full benchmark that is in the, well, it's not yet in the GitHub repository, but it will be by the end of the day. So we compare on the benchmark against all different string sizes. So as I recall, the 16-byte string, the standard library implementation is closer, but we still outperform it.
Thank you.
Yeah.
Hey, that was a great talk. Enjoyed listening to it. It's funny how much strings can really bring out the anger.
It's surprising, yeah.
I had a few things. Maybe some of these would be best offline.
Sure.
I did want to ask about the 16-byte string. I think the standard library small strings at 20, 22, 24. You said you use SIMD though. Where does the SIMD get used to? Is it like for string searching, like substring finding, or is there anything exotic using SIMD, or is it just trying to use vector intrinsics to move memory?
It is trying to use vector intrinsics to use memory.
Okay.
Yeah, things super exotic there.
And one other thing, I think the string class was more than 128 bytes. I think I counted 140, because there was the 128-byte buffer and then additional fields after it.
Mm-hmm.
Was that slide more of an example of what this kind of looks like and not what it actually looks like, or is that the way that it is?
No, that's the way that it is. There are some like using declarations that I took out just for like brevity to make it fit on a slide, but no, that's the actual way that it is. Yeah.
Yeah, I'll leave the rest of it.
Okay, sure. Yeah, no problem. All right, great. Well, if there are no other questions, thank you very much for coming to the talk. Oh, sorry, there are online questions. My mistake.
Oh, no, it just popped up. Does SIMDString support the same amount of methods and helper routines that standard string offers?
Yes, it does. Yeah, it's conformant with the standard string API. All right, great. Thanks, everyone.